Okay, hey folks, continuing along, we're going to explore the properties of these radial wave functions. But first, I just want to make sure we review those. So that was a pretty lengthy set of videos last time. So if you recall, we arrived at this solution for the radial component, which depends on some normalization constant times this factor when the electron is very close to the nucleus. This bridge for the electron being, at modest distances that we refer to as the Laguerre polynomials, and this decaying exponential for when the electron is very far from the nucleus. And from this Laguerre polynomial, we get the N and L dependence, as you learned in Gen Chem. And so now, as you can see here, we've got this whole set of complicated equations that describe our radial component. So let's see how to put that together with our angular solution, and then we'll explore the properties of these radial solutions. So for example, if we want to put together the wave function for the 1s orbital, which we recognize will be n is 1, l is 0, and ml is 0, then we can notate that as psi 1, 0, 0. And as a function of r, theta, and phi, we're going to need the r1, 0 radial solution, and we'll need the y, 0, 0 angular solution. So you can see we have those tabulated right here. So putting those together, we get the following. So psi 1, 0, 0 of r theta phi equals. So I'm just going to start tabbing it in. And I'm also going to note here our function rho for this system with n is equal to 1 will be equal to 2 times z times r over the Bohr radius, where for hydrogen, z is positive 1. So we could even simplify that further and write that as 2r over a naught, specifically for hydrogen. So putting that together, we have 2 times, and I'm just going to replace the z with 1 over a naught to the 3/2 power, and e to the negative rho divided by 2, which will be 2r over 2 times the Bohr radius. So, and then that's our radial function, and then times the angular function, that's just 1 over 4 pi all square root. So simplifying a few things here, we can see the 1 over root of 4 will cancel with the 2. So we can get rid of those right there. And then I'm going to rewrite this as the square root then. So we've got square root of pi, and we've got the square root of a cubed. So I'll just combine all those terms as 1 over pi a naught cubed. And that equals e. And then, of course, the 2's cancel to the negative r over a. And hopefully this looks familiar to you. This was the very first wave function that we played with in our Mathematica assignment, which is pretty cool. So now looking at a graph of these things, we see the following. And this is only looking at the radial. And I'm going to note here that we're going to have some equations for our nodes. So just like we did in particle in a box, total nodes goes as n minus 1. We're also going to get a condition for our radial nodes, which goes n minus 1 minus l. And then our angular nodes go as the total minus the radial, so everything that's left over, right? So looking at n equals 1 and l equals 0, we should gather there that that's 1 minus 1 equals 0 nodes. And we can see just that it is like a decaying exponential and does not cross the x-axis. So there's no place here where psi equals 0. So now if we look at the next entry down, n is 2 and L is 0, we can see 2 minus 1 gives me 1. So I have one total node. And that total node, you'll notice, has to be a radial node from the 2 minus 1 minus 0. And the radial node is right there. There it is, where psi crosses the x-axis. Okay. So, and then we don't count those nodes at the end because it's analogous to our particle in the box solution. We don't expect psi to be found infinitely far away from the nucleus. So now going to the n is 3 and L is 0, you can see we'll have 3 minus 1 equals 2 total nodes. And hopefully we can see from this picture that those are both radial nodes. There they are, 1, 2. So we don't have any room left for angular nodes. And now, just as a reminder, right, if you recall from your Gen Chem, the n is 1, L is 0, we call 1s. The n is 2, the L is 0, we call 2s. And the n is 3, L is 0, we call 3s. And you can see none of those have angular nodes because they've all got this spherical symmetry. And that's a little bit of foreshadowing. We'll see that in the coming lectures. So now looking ahead at n is 2 and L is 1, we are going to have in my total nodes 2 minus 1 equals 1 total node. We don't see that given on the radial profile, and that's because it's 2 minus 1 minus 1 for our radial nodes, which equals 0. So the only nodes that we have in this case is angular nodes. And we might recall that this is our 2p orbital, and that angular node is that like conical section that's missing out of the orbital, right? That conical section indicated by those angles there. Going up, we've got now n is 3 and L is 1. So that becomes a 3 minus 1 equals 2 total nodes. One of them will be radial from the 3 minus 1 minus 1 equals 1. And there is our radial node, meaning the other node is an angular node. And then finally, and right, so we know that that's 3p, right? And finally, for n is 3 and L is 2, which we should recognize as 3d, that's going to go 3 minus 2 equals 1 total node. And then from our radial node profile, we can see that that's 3 minus 2 minus 1, or 3 minus 1 minus 2. So 0 radial nodes, which means that one node that we have right there is an angular node. Okay. So that's it for this section. So I foreshadowed all the names of these orbitals. We're now going to officially learn those names. Okay, folks, I'll see you in the next one.